Albedo is a pretty simple concept. Basically, it's how much light reflects, right? Scattered is a big word for reflecting off of something, right? Maybe scattered means that it goes in all directions. I really should look that up. But so the more it reflects, the bigger the albedo. And albedos can be they can be given as a percent. They can be given as a pure number, right? So 10% would be an albedo of 0.1. 85% would be an albedo of 0.85, right? And so if you look at this, if it's got a high albedo, right, this has got an albedo of 80% or 0.8, right? It's reflecting 80% of the light. This dark surface has an albedo of 10%, so it's reflecting only 10%, which means, of course, that 20% is absorbed in this case, right? And in this case, you would have 90% absorbed, right? So, you know, what do you want? Well, if you live in a hot climate, it's nice if your roof reflects most of the light, right? If you're trying to collect energy for solar cells or something like that, they should be dark colored, right? To better utilize the sun, right? And then this is one of the greenhouse, climate change problems, right? Is that snow and ice reflects a lot of light. Water reflects not so much, absorbs. It's a very good absorber, right? And so as the ice in the Arctic melts, you tend to get more absorption, which that's a positive feedback loop. The hotter it gets, the less ice there is. The less ice there is, the hotter it gets, right? Okay. And you can look, these are just some albedos given to us. Oceans, dark soils are not very reflective, right? Pine forest, light-colored deserts, right? Reflect a fair amount, right? But ice, look at ice, baby. Ice is very good. Fresh snow, also very good, right? Another thing you'll notice with snow, too, is that the snow will tend to make sun cups like this. And that's because surfaces that are like little cavities like that tend to absorb more energy. And the more they absorb, the more they become a cavity. And the more they become a cavity, the more they absorb energy. Okay, and that's called sun cupping. You definitely want to go skiing before sun cupping happens, right? Let's look at some example problems. These are really pretty simple. Okay. Sunlight with an intensity of 1030 watts per square meter, and that's a bright sunny day. Allegedly, roughly 1400 watts per square meter strikes the atmosphere, right? And then you can figure this out from the intensity of the sun, or the luminosity of the sun, and the distance we are from it. This might be what makes it to the surface of the Earth, right? So they give that to us. It shines on a solar heater with an albedo of 6.2%, so it's not reflecting very much, right? So what is the reflected intensity? Well, that's easy, right? It's 0.062 times 1030, right? Let's do that. We can do that. 0.062 times. And that is, wow, I am just in scientific notation mode. I really don't like that. Okay, so let's go. That is 63.86. So 63.9 watts per square meter are actually reflected, right? So how much is absorbed? Well, there's two ways to do this, right? You can go 1030 minus 63.9. So 1030 minus the answer I just got, and get 966.14 watts per square meter, and that's absorbed, right? Right, you got to love that, right? Okay. The other way to do it is to go, the amount absorbed is just 1 minus 0.062, right? Times 1030. I tend to do this, I don't know why. So parenthesis 1 minus 0.062 times 1030. And that's 966.14 again, okay? What power is absorbed if the heater has a surface area of 16 square meters? Well, let's see, what is it? Its intensity is power divided by area, right? So area times intensity, this is your IA, right? Is the power, right? So it's going to be, this is how much is absorbed, right? So 966.14, and that's watts per square meter, times 16 square meters. So times 16 is 15,458.24 watts. And that's a heater. Keep in mind that your photovoltaics are not nearly that efficient. Basically, photovoltaics will turn something like 20% of the light that hits them into electrical energy, right? Yeah. All right. Let's look at the next example. I think there's another example here. All right. On a day when the solar radiation is 980 watts, and this is kind of, it's not quite as bright, right? Maybe there's haze in the atmosphere, right? My sister, who's a solar engineer, will look outside on a February day and go, oh my gosh, it's 300 watts per square meter out there. That's like a dingy day, right? Okay, how much power per square meter is reflected off into space from the oceans? Well, let's find the oceans. That's 10% is reflected, right? Okay, so 980 times 0.10 is 98 watts per square meter reflected. All right, how much is absorbed? Well, absorbed would be 1 minus 0.1 times 980. Right, so it's the difference, the remainder, or what is it? I don't know. What do you call that? Okay, so parentheses 1 minus 0.1, or I could, by the way, just go 0.9 times, right, 980. But I'd rather do this because I feel like I'm doing something fancier. So that's 882 watts per square meter, and that's absorbed. Right? Do the same calculation for fresh snow. Oh, right. So fresh snow. Where's fresh snow? There it is, 85. Ooh, I think there's a lesson here, right? So reflected is 980 times 0.85. And that's 833. And that's watts per square meter reflected. This is why you got to wear your sunglasses, right? You get burned on the bottom of your nose from that stuff, right? Okay, and then absorbed would be 980 times 0.15. The 0.15 being 1 minus 0.85, right? Okay, so 980 times 0.15. This is how much is absorbed. Is 147 watts per square meter, and that's absorbed. Okay. Yeah. All right.